everyone. It's really a pleasure to be here. And I know I've worked with quite a few of you before, so it's really nice to be able to kind of provide like a bigger picture perspective of some of the things that we do in a slightly more informal setting. I have some chemical equations, so I'm just warning you. But the intent here is to just make sure that you're able to kind of get like the big picture and really the gist of where we're going. There's still a long way that we need to really traverse to get to where we need to be. So I'm just going to show you how we are building to that point. So this morning, I'm going to talk a little bit about decarbonizing mining and concrete sectors. This is the shortest title I've ever had. I'll be honest. I like long titles, so I'll keep it to that. But I will touch on heavy industry decarbonization as a whole, and I'll talk a little bit about the motivation for why we do what we do. So over the course of the past, I would say more than a century, we've really seen tremendous innovations in how we recover energy resources, how we convert them, how we can store them even. But in the process of doing that, we haven't paid as much attention to our greenhouse gas emissions. We figured out how to treat our water, we figured out how to treat our soils, but we have not paid as much attention to how we can pull out greenhouse gases, which we're emitting in large quantities. And CO2, if you think about it, the argument that people make is that it's an acid gas, but it's something that trees use. So how can it be detrimental? But the thing with most things in life is that too much of anything is a bad thing, right? And that is something that we're seeing manifest in the climate. So a big part of the work that we do is on working on advancing solutions towards the energy transition and beyond, right? So what would an ideal world look beyond the energy transition, right? Hopefully we'll get to a point where the carbon stays in the subsurface. We've solved the carbon partitioning problem. The way I like to approach this challenge is that we don't necessarily have a carbon capture problem, we have a carbon partitioning problem. What I mean by that is the carbon that should be in the soil and the subsurface is actually in the air and in the ocean. So we really have to do what we can to put the carbon back where it's supposed to be, right? So we not only do we need to think about industrial solutions, but we also need to think about natural solutions. We need to think about the synergy of the entire carbon balance, right? So for that reason, in my group, we also work very closely with folks in CALS as well. I have a lot of experience in actually developing natural carbon solutions that actually pull down CO2 and then store it in a natural environment. As an engineer, I'm trained to think about things in boxes, inputs, outputs, how I can couple them and how I can get the most energy efficiencies and material efficiencies out of them. So it's interesting to be able to talk to folks on the other side. So with that said, as far as our future is concerned, we really want to be able to transport ourselves, eat, do the things that we want to do without a lot of emissions, right? So then the question becomes, where is the future of energy? Like, where are we going to harness our energy resources? And turns out that the solutions are going to look increasingly regional as opposed to being centralized. So right now, a lot of the energy infrastructure is very, very centralized. And as we move forward, especially if you're looking to decarbonize, we'll have to start thinking locally. What solutions make sense locally? Is it going to be geothermal, solar, wind? Is it going to be combination of a lot of these other solutions? Is there going to be energy storage involved? What is that portfolio of solutions going to look like? So a lot of the resources that we get from renewable energy are inherently local, right? So for example, the kind of solar energy that can be harnessed in Africa, we're not going to be able to do that in Ithaca, right? The kind of water resources that exist for splitting water to produce hydrogen that exist in Namibia, probably harder to do, where you have a lot of saltwater resources. Places in South America that have a lot of energy critical metals, they're already talking about, or Chile, for example, has gone ahead and basically banned privatization of private companies mining for lithium. They want to, they basically took it under the government because it's a protected resource. And what that means is that they're going to develop that resource in a way that is beneficial only to their country. So you're seeing a lot of those regional solutions that are coming into play, and just the way energy and resources has shaped is shaping and continues to shape, it will continue to shape the future of the energy transition. So I think it's really important for us to be cognizant about regionalization of some of these energy resources, where they exist, how we harness them, how we develop those partnerships. And increasingly, a lot of these resources are available in the global south, not necessarily the global north. Australia, which was once known for coal, has a lot of lithium as well. So how do we actually develop those partnerships, and how do we work with those countries is also very important. In addition to, of course, I'm not saying that there are no resources in the US, there's plenty of them, I'll touch upon that. But I think it's also important for us to keep in mind, our place in the world and everybody else's respective places in the world as well, and how all of this kind of fits together. A lot of the work that we do in our group is looking ahead and thinking about some of the energy and resource conversion pathways that we will need today and for the future, how we can at the same time capture, store, remove CO2 emissions. And this is really a big challenge because, as wonderful as the promise of renewable energy is, there's an article in the Wall Street Journal this morning about how mining companies are really struggling to manage their CO2 emissions because they are not able to switch to renewable energy because of lack of capacity. So this challenge is persistent, right? So we need as much renewable energy as we can. That will help us decarbonize quickly, but there is always a time lag with these challenges. In the meantime, the CO2 emissions are just skyrocketing, right? So how do we address these challenges? And then the question becomes, there is no such process as zero waste. There's always going to be some kind of residual waste. So how do we actually deal with that? So can we, first of all, minimize the waste and where possible, create a circular material economy, right? But then creating circular material economy requires energy. So in a world where there's abundance of energy, we will have solved the climate problem. In a world where we are energy constrained, we're going to continue struggling because of the coupled effects of carbon emission, as well as the need to, reach to a sustainable state of climate. Motivation for my talk, I'm going to talk a little bit about carbon management. And, oftentimes people distance carbon management as a thing in and of itself. But the reality is that it's very closely coupled to energy, resource conversion, industrial decarbonization. Granted, over the course of the past decade, there's been 50 to 60% penetration of renewable energy in the United States, which is wonderful. Electricity is probably going to all be converted into renewable energy. That is wonderful. But heavy industry decarbonization remains a challenge. And I'll talk a little bit about why that's the case, because there's actually a lot of chemical reactions that are involved that produce the CO2. It doesn't just come from burning of coal, right? You can circumvent all that, but then when the process of just producing cement, just the process itself, forget the fossil fuel that are needed to produce it, those in and of itself were highly, highly emissive. So how can we address that challenge? And even if we switch to clean energy or green carriers like hydrogen, those processes tend to be more favored at higher temperatures because they're endothermic. What that means is that they like to consume more heat in the presence of hydrogen. So even to use clean energy carriers for converting some of these materials can actually cost you more in terms of energy rather than less in terms of energy. So those are the things that we think about as engineers. We draw a box and we just, you could spend an entire lifetime just looking at decarbonizing fertilizers, entire lifetime just looking at decarbonizing mining, right? So to tackle each of these challenges is, it's really major. I'm going to talk a little bit about carbon management, but also resource recovery at the same time, opportunities and challenges in current state of the art, how CO2 capture and storage technologies fit in, how hydrogen fits in, and some of the key conclusions. And again, what I'm talking about here is a set of solutions which are not the only set of solutions. There's a wide portfolio of solutions, right? And then when we talk about regionalization, there are some places where some solutions fit a lot better compared to other solutions, right? So we just have to be very cognizant of that. So the need for scalable industrial decarbonization. So I always like to start my talk by saying that clean air, clean water, healthy soil, stable climate are the fundamental building blocks of life. Without that, there is no life. Forget human life, there is no life at all on this planet. So it's really important that we have that. But then abundant, low-cost, clean energy and resources are crucial for realizing a high quality of life, right? So these are the constraints that we live under, right? We want to have a high quality life, but at the same time, we need to preserve the resources that actually make up life itself. So how do we reconcile these needs in response to a changing climate? And with that said, there are some reasons to be optimistic. The first is that there are increasingly low costs of electricity from renewable energy resources. This can actually aid in the decarbonization of the electricity sector, which is wonderful. But then the question becomes, how do we abate CO2 emissions from industrial sources? What are even the sources of CO2 emissions? And how can we harness multiple emission streams to produce high-value products? So again, going back to the theme of actually closing the material cycle. And this is just a breakdown of some of the emissions, particularly the emissions that are very difficult and hard to abate, right? So iron and steel is about 5%, cement is 4%, there's aviation, which is 2%, long distance, 1%, shipping, variable electricity. So, assuming that we can electrify transport, we're on our way there. We're electrifying power. And then if we can get low-grade geothermal heat, we can handle buildings and residential and commercial, but these sectors remain particularly challenging. I'll talk a little bit about industrial decarbonization in the context of different sectors. So if you look at just the industry, so these are direct CO2 emissions from industry, and this is in a net zero scenario. And this is starting all the way from 2000 to 2020, and then getting to 2030 eventually. And what you'll see is that iron and steel is a big contributor. There's cement, there's chemicals, petrochemicals. This is all of the industry, and pulp and paper is here. Okay? So just, if you break these down, you start to realize that these quantities are not trivial. And if you look at the final energy consumption by fuel, they consume a lot of coal, oil, gas, somewhat a fairly significant quantity of electricity, but no way as large as these three quantities, and some heat. Okay? And as we project out to the future, this is what that looks like. We intend for there to be a little bit more hydrogen. So even though you see all the wonderful news about hydrogen, it's still only going to be the small red sliver right there. By 2030, it's going to be a small piece of that. There's still going to be coal, there's still going to be oil, there's still going to be gas. Electricity is going to increase. So it remains challenging, right? Even by 2030, a reliance, at least a projected reliance, is going to come from hydrocarbons. That is what is, this is not me saying it, this is what IEA is saying, right? So this is what we face when we are thinking about industrial decarbonization, okay? So direct CO2 emissions are persistent. So CO2 emissions will remain in 2030, and these need to be managed. So now we have to start being inventive, which is what engineers are good at doing, right? So now let's think a little bit about how I can help decarbonize wind, solar, energy storage, and battery technologies. So what is really needed for those technologies is a decarbonized supply chain of the metals themselves, right? So it's not enough to say, hey, I have a solar plant and it's working amazingly well. Because a lot of the solar panels that are used in the world today, they come from China. And it's in the open use that there's a lot of fossil fuel that's actually consumed to make the solar panels. So it takes some time to actually recoup your carbon budget. You have to run it for a few years to recoup the carbon budget. Same thing for windmills, right? The processes for producing rare earth elements that go into windmill magnets, extremely emissive. And that's because I work on these processes every day. I understand the separations, and they're not trivial. So in addition to greenhouse gas emissions, they also use a lot of organic solvents, which are not very benign. And these metals make their way into soils, and there's evidence of pollution everywhere, right? So in a world where we reduce our dependence on fossil energy resources and increase our reliance on mining, we're basically shifting the environmental burden, if you like, right? It is said that mountains that actually have some of these energy critical minerals might actually be, turned into rubble. The entire landscape is going to change given the kind of defossilization that is needed. right? So managing the environmental impacts is really critical. This is not something that I am saying. This is something that my program directors at ARPA-E and DOE tell me, right? The kind of material cycles, the kind of material transformations are needed are going to have big, big impacts on the world, right? So just to give you a little bit of perspective, talk a little bit about mineral intensity here. These are all some of the different metals that are used. There's a lot of copper that is used here. This is for wind power. This is these are just different turbine types, so you don't worry too much about the jargon. This is just mineral intensity for wind power. A lot of copper that's used, a lot of zinc that is used, manganese, some chromium. There is some nickel, molybdenum, rare earths, and there are other metals. And if you look at the rare earths themselves, these are some of the rare earths that are used, right? So this is just taking this little sliver of purple that we have and kind of blowing that up a little bit more. So to produce 1 megawatt of power is going to require, in some scenarios, particularly for this type of turbine, it's going to take about 200 kilograms of rare earth metals, right? And just to give you a sense of some of the concentrations that we work with, so if we mine a rock, the quantity of rare earths that we have in a rock is 200 ppm or less. So what that means is that I have to go through 1 million particles to find 200 particles of the rare earths that I really need. So imagine the amount of processing that is needed. Right? So this is really not trivial. So sustainable recovery of energy critical minerals, and here I call that rare earth metals, is crucial for limiting primary mining of ores. Right? So I have not shown here, but there's projected increases in primary mining that is needed, but in addition, we also need to mine from what is already there. That's called urban mining. So how can we actually move towards an urban mining future is also really important. And another challenge here is that we have all of these different metals as well that have a lot of CO2 emissions per ton of metal, as you can see. Cobalt tends to be highly emissive, both from the mining and this is from the processing. Okay? So it's not just the mining piece, it's also how we process the metals. It can be very, very emissive. And similarly from battery technologies as well, depending on the lifetimes of vehicles, huge emissions from mining. So again, more data here on CO2 emissions. This is looking at aluminum, cement, and pulp and paper. With that said, I'm going to jump to this slide here, which talks a little bit about overlaying all of our demand for critical metals with the need for managing carbon solutions, right? So how many of you have seen this figure before? Okay, this is a really important figure from the perspective of the 2030 project. And the reason is because this actually shows how much effort we need to put in to really bend this climate curve. Okay, so this curve represents CO2 emissions as usual. So if we just, go with conventional rate at which we are deploying renewable energy, you'll see that the CO2 emissions will kind of grow unabated, and maybe by about 2030, there's a small dip. That's too late, right? By then, we will have seen huge increases in temperature. But then if we need to keep the temperature below 2 degrees centigrade, we have really no choice but to bend this curve down as quickly as we can. So then the question becomes, how do we try and bend this curve down? So you see this difference here, this delta, that corresponds to conventional abatement technologies. All the technologies that we can use to abate CO2 emissions. And here, in blue, you see technologies that are known as negative emission technologies. So these are technologies that actually put away more CO2 emissions than what they actually emit, right? So now we need to it's not enough for us to develop processes that will cut back on CO2 emissions. We actually need to start developing processes that will store CO2 emission. That is what that is telling us. So if we actually have to try and get to this 2 degree C scenario, to get to a scenario where temperatures don't rise more than 2 degrees centigrade, we will need net negative emission technologies. So here you see afforestation, reforestation. You'll see other negative emission technologies. This is capturing CO2 from oceans, using algae, for example, or engineered processes, capturing CO2 from air, right? Using bioenergy with carbon capture storage, for example, or just using biomass to capture CO2 and then just burying it. You may have heard of biomass burial, for example. Those are all solutions that come under negative emission technologies. Okay? So this is gaining a lot of importance to the point where people are willing to put a price on it, right? So for example, we launched our startup, which is Carbon to Stone, and for every 1 ton of carbon that we remove, we get paid about $100 per ton, because it's becoming that important to actually remove the carbon emission, right? And the less we do in terms of managing carbon emission, the more valuable my company becomes, right? I'm sorry, I hate to be a capitalist here and make money off of climate, but that is the sad reality, right? Just to quickly walk you through the societal challenge. So how do we continue meeting a growing demand for energy and resources while reducing detrimental environmental impacts? Technological challenges, we need to do a lot of science and engineering here to really develop the next generation of processes with inherent environmental controls that are baked in to the process itself. And the scientific challenge is that we still don't really understand a whole lot about how fluids are organized at solid interfaces, for example, or how the structures and the morphologies of these materials, particularly carbonates, how that evolves in a lot of these different conditions. And then all of this really fundamental information is really important to inform material and energy conversions at scale, right? So this is now coming back to why students need to take all of their Chem 101 classes and go through the engineering curriculum the way it's designed, so they can actually get to the point of developing technology. So with that said, as engineers, we're very good at conceptualizing, drawing a box, figuring out what goes in and how do we get stuff out. So this is an example of taking acid gases, producing mineralized solids, taking many, many gas streams, separating out those gas streams, taking wastewater, producing clean water. And this is in response to some kind of a trigger, right? Then the challenge is, how can I place this in the context of carbon management and metal recovery, for example, which is really important for decarbonizing. So the scientific challenges here, I know this is a lot of verbiage, but to walk you through quickly, we need to develop new insights into fluid organization and transport properties. We need to understand, for example, how carbonates are evolving as we try and produce them, how, as we try and recover the metals of interest, how the substrate is changing, how the metals are precipitating, because all of that controls how we actually develop the engineered process of interest. And then we need to determine the impact of experimental and measured data, and this is where hopefully we can harness some of the advances in AI and machine learning to help streamline the way we actually get to a scaled-up facility. Since we are here to talk about solutions, a little less about science, right? I'll skip these two parts for now, and I'll get to the solutions part of it, because I think that's really something that people get very excited about, and they want to know, what is it that we can actually do? And the motivation for doing what we do part of the motivation comes from this figure here. So this figure was published in IPCC report in 2019. So this shows the cost per ton of CO2, and here you'll see a wide range of different solutions. Let's start with the ones that we are most familiar with, afforestation and reforestation. Doesn't cost much, less than $50, right? Quite a bit, potential is pretty good. It ranges from about 0.5 to about 3.5. But I want you to put this in perspective, that we are emitting at least anywhere in the neighborhood of 35 to 45 gigatons of CO2 per year. Okay? Let's keep that at the back of our mind. So this is potential carbon storage per year. So this will get us partway there, but not all the way there, especially if you're emitting 35 to 45 gigatons of CO2 per year. Soil carbon sequestration will get us, a fair amount in terms of carbon storage. Again, cost is reasonable, but then quantification becomes a challenge, because if I store my carbon, how can I be certain that my microbes are not eating that up and producing CO2 back into the air? Verification, monitoring becomes very, very important. Uncertainties exist there as well. Then there is enhanced weathering, which is rock dust distributing rock dust, which is something that Dean Ben Hulton does quite extensively. So this basically involves crushing volcanic rock and then distributing that in soil. So CO2 is an acid gas, right? And from Chem 101, we know that to balance an acid gas, you need a base. So the base actually comes from the rock dust. So what we can do is, so if I introduce a metal species, a calcium or a magnesium species into the soil, then I can now grab some CO2 from the air to balance the charge. So that's how rock dust works. Okay, so rock dust is about distributing that ground alkaline powder into the soils. Then there's bioenergy with carbon capture storage. This is an interesting one. It has a big potential, but costs are high. And it's interesting because a lot of, for example, if we take coal-fired power plants, right? The reason why we get very upset with them is because coal is fossil. Once you burn it, you can't renew it, and the emission is out in the atmosphere forever. But if you put in bioenergy instead, right? If you put biomass instead, and now if you capture and store the CO2 somewhere, then that has the potential to be net negative. Now, I'm not talking about public opinion, community impact, just talking pure engineering here, right? Let's just, if I draw my box, am I able to get to net negative? And turns out you can with bioenergy, not advocating for it, but you can get there. And then there's direct air capture and storage, which, people have a lot of strong opinions about it, but oh well, the less we do today, the more direct air capture we need to do in the future, right? When I started out as a graduate student, I was told that this is an insurance technology. This is a technology that you use in the worst case scenario. You have it in your back pocket, you develop it, and you deploy it only when you really need it. Because it's expensive, it takes up a lot of land, takes up a lot of infrastructure, may not get the kind of acceptance that you want. But over the course of the past decade, we've kind of just been waiting for the promise of renewable energy to materialize. We were hoping that businesses would act for the good of the planet. That hasn't worked out the way we thought it would. So now there's a lot of interest in developing direct air capture technologies, right, for that reason. Might continue that way if we do less about deploying a lot of these low-hanging fruit solutions, right? So with that perspective, the question becomes, how do we harness novel technological solutions to lower the cost of carbon management? And the reality, and I'll talk about this a little bit later, is that a lot of, so there's Scope 1, Scope 2, and Scope 3 emissions. Scope 1 emissions are those emissions that get directly produced, say, during iron and steel making, so they have to figure out a way to address that. Scope 2 is perhaps by replacing with renewable energy, and Scope 3 is in your raw materials that you bring in, right? It's all those really hard to quantify emissions. So the point that I'm trying to make here is that even data centers like Amazon, Meta, Microsoft, they have an enormous carbon footprint. It's not Scope 1, it's Scope 2 and Scope 3. So Microsoft is actually, surprisingly, the biggest investor in carbon removal these days. Who would have thought? But because of their footprint, right? So it's important for us to kind of put all of these things in perspective, right? So anyway, we can talk a little bit about carbon storage. There was a DAC Hub announcement that came out. A lot of interest in sticking CO2 in the subsurface environment. People don't like it in New York State. I get it. People in Texas, Louisiana love it because it's a way for them to, have some revenue that comes out of it, and they're very comfortable with living with fluids underground, right? So there's different ways in which the CO2 can actually interact with the rocks, just to give you some perspective here. If you have a more reactive rock, like the calcium, magnesium, silica that is used in rock dust, if you inject into those formations, then that CO2 can get mineralized very, very quickly within about a year. And it can get stored as stone in the subsurface environment. If you don't have these kinds of rocks, then most of the CO2 actually dissolves in the water, in the pore fluid. Basically lives like soda water in the subsurface environment, right? And then over time, if it encounters the calcium or magnesium ion, it's going to mineralize. Just wanted to give you a perspective on some of the existing technologies. So this is conventional carbon capture. So conventional carbon capture has been around for 100 years now. Okay, this is not something that is so new. It's something that's been around. The earliest patent was filed in 1930s. And the idea here is that CO2 is an acid gas. Let's put in a base. Base captures the CO2. I can drive more CO2 into the solution. Take that solution over to this other system, heat up that solution so I get high purity CO2. I regenerate that fluid, and then I can reuse that fluid again and again for CO2 capture. The idea was that we can produce high purity CO2, and once you produce high purity CO2, you can use that for chemicals, fuels. You can use it to make products, polymers. You can stick that CO2 in the subsurface, or in our case, we can mineralize it. We can turn it into stone, right? So I looked at this, and if you look at these processes, you'll notice that there is unit operation 1, unit operation 2, unit operation 3. I need 3 operations to get to this if I'm starting from air or flue gas. So I stared at this figure long enough to figure out a way to combine these 3 into one process, or in some cases, these 3 into 2 processes. And that actually gives me enormous gain in terms of the capital expenditure as well as the operating expenditure. So that's really the innovation that we came up with. And the way we did it was that we bypassed the step of producing high purity CO2 in the gas phase, and we combined these 2 steps together. So think about this. I have CO2 in the gas phase. I push it into the liquid. Now if I put a solid in, the CO2 that's in my liquid phase, if it can react with the CO2 in the liquid phase to produce a carbonate, then I basically stored that CO2. And then this medium that was used to capture the CO2 gets regenerated. Right? So that's really the idea. So I decided not to release the CO2, but instead keep that in the solution and combine it with using an alkaline solid to help with the precipitation. What that means is that conventional approaches for carbon management have many, many steps. So you see this is the relative energy. So to produce a carbonate in solution, it's thermodynamically feasible. To produce pure CO2 consumes energy. To compress that CO2 consumes more energy. And then to produce products like polyester, polycarbonate, or methanol, especially polyester, consumes some energy. But if I can make a carbonate, it's thermodynamically downhill, right? It's net negative, which means that it actually produces energy instead of consuming it. This is the reason why we actually see calcite caves. We actually see natural calcite deposits, right? Because Mother Nature likes it. It's a thermodynamically downhill route. So my job is to just take what Mother Nature likes and speed it up as an engineer. That's all I do, right? And to come up with clever ways in which I can combine different processes. And now the question becomes, okay, all of this is great, but we are emitting 45 gigatons of CO2 into the atmosphere every year. Where is my basicity so I can actually store that CO2, right? So in the United States, it turns out that there are quite a few places. If you look along the coast here, you'll see there's magnesium-based ultramafic rocks. There's some rocks here along the western coast. There's a huge deposit here, which is known as the Columbia River basalt. So one of my closest collaborators is Pacific Northwest National Laboratory, PNNL, and they are located here. Right? They do a lot of work with this resource here, right? Because not only is this a good carbon storage site, it's also a very good site for recovering critical metals, turns out. So we have some projects with them on how we can store CO2 and separate critical metals at the same time. And then there's places in South America where we can do this. The Oman pegmatite is a very famous one, something that Columbia scientists have been studying for many years now. So there's no shortage of places where you can do this. There's certainly places that you can do it, just that public acceptance might differ wherever we decide to implement this technology. So then the question becomes, okay, let's look at the energy transformation, right? So I'm going from carbon to carbon dioxide, which is a low energy molecule. And now I'm taking this low energy molecule and turning it into an even lower energy molecule, which is a carbonate. So what you'll see from others is that, let's just say Dimensional Energy or some of the other folks, what they do is they have carbon dioxide. Now they have to pump in energy to make a fuel or a chemical. They have to pump in energy and they have to supply hydrogen. So it's really important, again, to assess the energetics. That's why regionalization, again, becomes very, very important. Am I able to harness low-carbon electricity, especially if I'm going to go through a thermodynamically uphill route? How much temperature do I need? Where am I going to get that from, right? All important questions. So very quickly, these are just two locations. So this is a place in Oman that's actually been serving as a natural carbon sink. So these are large deposits of olivine. And what you'll see here is that there's some water films on these olivine surfaces where some magnesium has been accumulating. And that accumulated magnesium is actually driving CO2 from the atmosphere into these alkaline sources. Okay? And then here we have the Belvedere, in the Belvedere Mountains in Vermont. These are known for their serpentine tailings. So serpentine is a hydrated magnesium silicate. It's mined for nickel. So once the nickel was extracted, these mine tailings were just deposited. People didn't want to touch them after that. They're a fantastic resource for carbon management. So these resources already exist, right? So why don't we use them instead of having them accumulate in our backyard as mine tailings? And that's what we decided to do. And then we also started to look at all the alkaline resources that come from heavy industry. So we have mine tailings. Here we have coal fly ash, steel slag, cement kiln dust, aluminum. Aluminum production produces red mud. So a lot of industries produce both CO2 emission as well as the alkaline resource that is needed for carbon management. So this is the scary chemistry part, but I'll walk you through it. So there are three boxes here. And the first one here is, let's just say I'm producing biogas from anaerobic digestion, right? So there's going to be some CO2 and methane that's produced. Now, can I develop a technology that will capture and convert the CO2 into a carbonate and just give me the rest of the gas of interest, right? And this is true whether it's for gasification of biomass, in which case we produce hydrogen, and that's what we are trying to do here. And if you look at the temperatures, they're typically less than 90 degrees centigrade, so not very high in temperature, so you can actually harness geothermal heat even for a process like this. And then there is about more than 80% of the hydrogen that we use today comes from a process known as steam methane reforming. So steam methane reforming takes methane, converts that to hydrogen, and now we are talking about a hydrogen economy that basically comes from a carbon source. That's very, very carbon intensive. We don't want that. If we have to do that via electrolysis, that also consumes a lot of electricity. So a lot of innovation is needed. So then the question becomes, if I have biomethane as opposed to fossil methane, can I then react some of the precursors with the alkaline resource so I can trap the carbon dioxide and produce high purity hydrogen, right? And also, if I start with organic wastewater that has a lot of organic molecules in them, can I break them down to produce hydrogen and capture and convert the CO2 as calcium or magnesium carbonate? So just to quickly walk you through, again, more scary chemistry here. So CO2 in the gas phase, if there is no alkaline solvent, we produce bicarbonate species, soda water. This is a soda water chemistry, right? Now, if I introduce some kind of alkaline source, we'll call it an amine because those are the ones that are known to capture the CO2. So we produce a solution now that is concentrated in carbonate species. I can react these carbonates with my calcium or magnesium resource. I can produce calcium magnesium carbonate. And because I am basically taking up or depleting my solution of the carbonates, I can regenerate my solvent back again. Okay? So we did quite a bit of work here. We showed that if we have a lot of calcium oxide, we can convert 100% of that into carbonate. This happens in less than 3 hours with a wide range of different solvents. So the ones that we found to be effective are amino acid salts that we actually have in our bodies, right? So they're environmentally benign. So you can get 100% conversion there. With calcium silicate, a lot of this is actually present in alkaline residues. We get about 35% conversion. So if we take coal fly ash, and we have lots of this accumulating in our backyards, right? Not environmentally benign. And if we just put that in pure water, we only mineralize about 15% of it. The moment we add our solvent into the system, we mineralize about 45 to 55% of it. So then we're like, okay, this seems to be working, and that's when the program directors got excited. Because if it were up to me, I'd just be like, well, I want to make sure that my students graduate. Let's put the startup idea aside for a little bit longer, right? But they really pushed me to do this. They really pushed me to commercialize the technology. So that's why we came out with Carbon to Stone. So they wanted us to do some economic analysis to get a sense of how much our processes would cost, right? So if we did this with flue gas, so let's just say there's an iron and steel making plant emitting a lot of CO2 emission. They also have a lot of slag that is produced. If you implement our technology, the costs are in the range of about $35 to $55 per ton. If we did this directly from air, which is much, much more dilute, the capital expenditures tend to be much higher. The costs are about $83 to $126 per ton, about twice as much, roughly. So the target customers here are heavy industry, iron and steel. I should also add cement here, as well as mining. And then for the carbon removals, data centers, Amazon, Meta, and Google are very, very interested. Every entity has their own net zero targets, right? And for them, their core business is to run a data center. And they have to keep running these data centers 24/7, right? So they'll use whatever cheap electricity that they can get, and oftentimes the cheapest electricity tends to be a fossil-derived electricity, enormous carbon footprint. So their shareholders are kind of breathing down their neck, and their investors breathing down their neck, asking, okay, can you be a little bit more environmentally responsible about this? What are you doing about this? So that's hence the motivation for investing in carbon management. So we act in a very contextualized manner, right? For our solution to be viable, it has to exist in a world where there is no policy driver and there's only a market driver, right? So we are motivated by developing a technology that can stand on its own 2 feet without any state policy, without any federal policy, with basically nothing. So that's our constraint. And it's and there are plenty of other companies that are doing exactly what you said. You know, they're heavily reliant and they're kind of sweating it out right now about who's going to come into the government, you know, who's going to be running the government in another year and a half or 2 years from now. But for us, the fact that we are making carbonates and there's a huge demand for carbonates, and we're doing this with their CO2 emission, with their waste heat on their site, right? And we're taking multiple emission streams and producing useful products so they can do less landfilling. That's all pluses for them, right? You don't need a policy to make it happen. You just need somebody who is sustainably minded and who's thinking about the enormous landfill footprint of managing alkaline residues. And in pretty much all the states, they actually have to pay a lot of money to landfill. It costs about $55 to $60 for landfilling alkaline residues. And we've done away with those costs for these companies. We want those residues. So now we want the residues, we want the emissions, so we can produce high value products that can then go back into the market for them. So, not speaking about the entire landscape, but just speaking contextually about how we're approaching this. A quick point here is that, so I'm an engineer, and all engineering comes with constraints. So the question here is, what are we constrained by here, right? So what is giving here? So it turns out that in our process, we have to be very, very mindful of the solvent regeneration, right? So how effectively are we able to reuse the solvent, and how are we minimizing the amount of solvent that we need per cycle? And turns out, and we did some life cycle analysis, and what we showed here is that if you get to about 93% or higher of solvent regeneration per cycle, that is, if we lose less than 7% of the solvent per cycle, we are in business, right? We can actually be in the carbon removal business and in a business that's actually generating revenue. And similarly, how much reactivity do we need to get? So if you're reacting a lot of the solid in producing carbonates, that's actually ideal. We don't want to get low reactivity, we want to get high reactivity. And then the question becomes, once I make my carbonates, what do I do with them? So here we have some data that shows the compressive strength of various cementitious materials, just for comparison. So this black line that you see here is ordinary Portland cement. This is just what we have around us today. If we substituted about 10% of that with carbonated slag, you see there is a significant enhancement. The compressive strength almost doubles, right? If we substitute it with silica, which is also a byproduct of our process, over time we see a significant enhancement. So this really gave us some insight into how we could be using our carbonates, right, as supplementary cementitious materials. And especially if you're capturing CO2 from air and putting those carbonates into cementitious materials, you could actually have net negative cements, right? So that is where we are headed with this. If you're capturing CO2 from flue gas emission, that is not net negative. At most, maybe you'll get to net zero, but that's not negative. But to get to a negative emission scenario, we need to produce very high strength cementitious materials using CO2 that we capture from air. So your question points to how stable are these carbonates, right? So calcium carbonate doesn't decompose until 800 degrees centigrade. So you really have to take this and put it in a volcano for this stuff to decompose. Or in acid rain conditions. If you go to pH like 2.5 or less, then they start to decompose. Hopefully we don't encounter those scenarios, right? Low risk scenarios, in which case they're going to be quite stable, right? Which is one of the appeals of carbonates, is that not only are they thermodynamically downhill, but they're also very stable and very environmentally benign. Just to give you a quick sense, coming back to your question about policy drivers, right? Or is the technology going to stand on its own 2 feet? So the costs here that I've shown are pure cost, right? So there's no revenue. This is just the cost for implementing a technology and how much it's going to cost us to actually remove the CO2. And these are all the different revenues. So I'll start from here. In terms of revenues, we can get about $20 per ton of carbonate-bearing aggregate. We can get more than, especially if you're separating any metals that are present, which is true with some alkaline resources. We can get more than $1,000 of valuable metals per ton of waste. We also help eliminate about $55 to $60 in tipping fee for landfilling. And these credits are just thanks to the IRA that came out last year, right? So according to the IRA, we can get about $85 per ton in credits for carbon storage from flue gas. So we do carbon storage and we do the utilization. So we use the carbon and we store the carbon. I'm going to very briefly touch on some more futuristic approaches that we are developing for producing low carbon hydrogen. So when I was a graduate student, I worked a lot with geologists and geochemists, right? And for them, it was just doing science for its own sake, right? But I'm the engineer, and I'm like, okay, we're developing this reaction. Where can I stick it? What can I do with it, right? So I spent a lot of time coming up with ways in which I could mineralize a mineral known as olivine. It's magnesium silicate. And I could react it at high temperatures, more than 200 degrees centigrade, and high pressures, 10 to 20 atmosphere, to produce carbonates. And, we published some papers. It was really nice, and I shelved it for a couple of years. I was doing some postdocs in other groups. And then I came back to it, and I realized that these conditions at which mineralization takes place is ideal for integration with reforming of biomethane, right? So all these reactions that I was studying, like deep in the subsurface for carbon storage, I could actually integrate with a process for producing hydrogen, today, right? And the way it works is that, so this reaction here where you have carbon monoxide, which is produced from methane, and steam, so these two come from biomethane. We produce CO2 and hydrogen. And now if I introduce magnesium silicate, that can then react in a few steps to produce magnesium carbonate. So all the carbon, that is carbon monoxide, I'm partitioning that or converting that into a carbonate. And all the hydrogen that's in my steam, I'm producing hydrogen out of that, right? So it becomes at least on paper, it's an exothermic route, right? So that's nice. And then what I decided to propose for my DOE career was to take the water-gas shift reaction, which has been developed for more than a century now, and couple that with this really new pathway for carbon mineralization. So that way, whatever hydrogen is produced, I'm pulling the CO2 actively, so I can produce high purity hydrogen and I can store the CO2 at the same time. So this is just some results, some preliminary results. So this is the base case. So if you look at hydrogen, we get about 29% hydrogen in the gas phase. The moment I introduce calcium silicate, I can enhance the yields to about 51%. When I do not have calcium silicate in the system, I have about 22% CO2. When I introduce calcium silicate, I'm able to suppress that to about 11%. Right? So this is not fully optimized, but at least it's trending in the right direction. So I have a PhD student who's working on this right now. Another PhD student of mine, Prince, is taking organic wastewater or water that comes from algae processing, right? So algae does an amazing job of capturing CO2 and producing biomolecules, right? So there's high-value biomolecules, and then there's everything else. And then there's an enormous amount of wastewater that needs to be processed that has maybe only about 2 to 3% of this biocarbon, which you're wondering, what am I going to do with it, right? Should I just let it go to waste, or can I produce hydrogen out of it? So what he decided to do was he started doing some reactions of taking low-value organic biomass oxygenate aqueous streams, not solids, but aqueous wastewater, and converting that to hydrogen and sticking the carbon into carbonate, right? So we've been quite successful. He was the first person in 24 years to win the Link Energy Fellowship, which is administered through Dartmouth. So there's only 3 of them that are given out, 3 to 4 of them that are given out every year. It's more competitive than NSF fellowships. So he's very talented. So just to give you a sense of how these processes work, so we did some thermodynamic calculations, and this is the best case scenario. The best case scenario is where we have one competing reaction where this methanol, waste methanol, can get decomposed to produce methane. So if we shut down that methane pathway, then the other pathway, which is a pathway to produce hydrogen, becomes active, right? So the key challenge is to shut down the methane pathway. And whatever CO2 we are producing, we want to capture and convert that into a carbonate. So there's 2 things that we need to do. Use an alkaline source to capture the CO2 and shut down the methane pathway. So to shut down the methane pathway, we can use a catalyst that will cleave the molecule only where we want it cleaved. So these are intelligent materials. And then we can produce hydrogen and CO2. And here in the gas phase, we have the sorbent that captures the CO2. So effectively, all you're left with is hydrogen in the gas phase. There should be no CO2 in the gas phase. So this is a lot of data, but the key things that I want you to pay attention to is that if you look at this data here, you'll see that the amount of hydrogen that we get is only about 2%, and there's a lot of CO2 emission, right? But the moment we put in a nickel catalyst and we also put in our alkaline resource, which is calcium hydroxide, we produce about 80% hydrogen, and we suppress all the CO2. There is no red here, right? And there's a little bit of methane that shows up, but very small. Okay? So we can do this with a nickel catalyst or a platinum catalyst, which shuts down the methanation path. So by definition, a catalyst is a material that does not get consumed or produced. You can just reuse it over multiple cycles, right? So again, more data here to show you the carbon capture kinetics. The triangles here show you the formation of very stable calcite, which is calcium carbonate. There is some oxidation of the catalyst surface, so we are looking at replacing the catalyst surface that we're using right now with something that's a little bit more sturdy. So we published this, and right now we are looking at using a ladle slag material that we get from Nucor as our alkaline source. And when we do that, our yields, this is the first set of tests that we did, we get about 45% conversion, and we capture and store the CO2 as a calcium carbonate. It works very, very well. In terms of where we're going with this for next steps, we're looking at ways in which we could effectively break down. We could use electricity instead of heat. A lot of the processes that I talked about based on heat. So here we are looking at ways in which we can use electron transfer to basically produce high purity hydrogen. And if you're starting from a carbon source, whether that's an oxygenate source or some kind of waste carbon source, you want to capture and store that CO2 in the form of carbonate. So just a few conclusions here. So I've shown different pathways in which we can manage carbon emissions, some of which we are scaling up, some of which are still at a very, very small lab scale, some of which have a lot of interest from industry partners, and some of our industry partners are interested in other solutions as well, but they're waiting for us to, basically show proof of concept before they can maybe provide a little bit more support. Looking at ways in which we can use catalysts, for example, to specifically cleave along certain surfaces. And just wanted to kind of provide a forward-looking motivation with electricity getting increasingly low carbon as well as cheaper. We want to start developing the electrochemical analogs to all of the processes that I just talked about. So with that said, just wanted to express a warm thanks to my research group. I did not talk about all the work that we're doing with lithium separation, rare earth element separation. We're developing a lot of functional materials to do that as well. Hopefully that will be a conversation for another time. I wanted to keep this a little bit more bite-sized this time, which still took a long time. So very grateful to my research group as well as extensive funding sources. And thank you so much for all the generous coverage that you provide for the work that we do.